Hi friends, in this video we are going to discuss about construction of induction machine. Can you tell me what is first part? What is first part? Yes, stator frame. This is also called as yoke in our DC machine, but don't call this here, right? This is called as stator frame, first one. This first one and this first one both are same, the stator frame. This is cross-sectional view and this is horizontal view. Cross-sectional view of the machine and horizontal view of the machine. The same ports will be here. The same ports will be here also. Actually here also. The same ports will be here. Okay. The first one is the stator frame. And second one is the stator core. First one is the stator frame and second one stator core, which contains stator winding, and third one is the air gap between stator and rotor. And fourth one is the rotor core. And fifth one is the shaft. And here, what are these? These are the slip rings. These are called as slip rings. This is the constructional details of our induction machine. See here clearly. Right. Now, first one. Take the first one. Stator frame. Stator frame. Can you tell me stator frame made up of? Stator frame made up of cast steel or cast iron. The stator frame made up of cast steel or cast iron. What is the purpose of stator frame? The stator frame acts as outer protecting layer. This is act as a outer protecting layer. Nothing but it protects the machine from outer surface. It protects the whole machine. Generally, this is made up of cast steel or cast iron. It is act as a outer protecting layer, and also it provides mechanical balance to the machine. And also, this is similar to DC machine's yoke. Everything is same. Yoke also made up of cast steel or cast iron. This is also made up of cast steel or cast iron. The purpose of yoke also, it acts as an outer protecting layer and provides the mechanical balance. And here also same. So this is similar to DC machine's yoke, but what are the differences between them? In DC machine, for example, this is my DC machine. Generally, this part is called as yoke. In DC machine, the yoke provides the return path for the flux. But in our AC machine, in our induction machine, the stator frame does not provide any flux path. There is no any flux path here. But in our DC machine, the yoke provides the return path, a low reluctance path for the flux, in DC machine. But in induction machine, it does not carry any flux. That's why this is similar to DC machine's yoke, of course, but here the yoke provides a low reluctance path for the flux, but the stator frame does not provide any flux path. They are asking question, which is need to laminate, yoke or stator frame? Generally, both are no need to laminate. But even though in DC machine nowadays, in modern DC machine, yokes also laminated in order to improve the efficiency up to 99%. Generally, because the yoke also provides a low reluctance path, right? The yoke also provides a return path for the flux, right? That's why to reduce the eddy current losses and hysteresis losses, nowadays we are going to laminate this yoke for DC machine. But in our induction machine, no need to laminate our stator frame because it does not provide any flux path. It does not provide any flux path. That's why no need to laminate. Right? This is about stator frame. Stator frame made up of cast steel or cast iron. And it acts as an outer protecting layer and it provides the mechanical balance. This is similar to DC machine's yoke. But it does not carry any flux. That's why no need to laminate. This is about simply the stator frame. Right, sir? Stator frame. First one completed. Next, second one. What is second one? The stator core. Now, can you tell me the stator core made up of? Tell me, sir. The stator core made up of CRNGO silicon steel laminations. What is that? The stator core made up of CRNGO silicon steel laminations. Stator core made up of CRNGO silicon steel laminations. CRNGO silicon steel laminations. CRNGO silicon steel laminations. Stator core made up of CRNGO silicon steel laminations. Generally in stationary machines CRGO, in rotating machines CRNGO. What is stationary machine? The transformer. In transformer we are using CRGO. Other than transformer, generally we are using CRNGO, cold rolled, non-grain oriented. Silicon steel laminations. Let's discuss about laminations. Tell me what is meaning of laminations? Laminations nothing but a big part divided into or cut into small parts. Nothing but a thin layers. A parallel thin layers are simply called as laminations. Generally, a parallel thin layers are generally called as laminations. Generally, the core may be like this. For example, now we have to like this, cut it into many parallel paths. Those many parallel paths are generally called as laminations. Okay. Generally, what is the thickness of laminating plates? Generally, the thickness of laminating plates 0.35 or 0.5 millimeters. 0.35 or 0.5 millimeters for each plate. This is for 50 hedges range and this is for 25 hedges range. This is for 50 hedges range and this is for 25 hedges range. The thickness of laminating plates. 0.35 to 0.5 mm. Okay. What is the use of laminations? Tell me, sir. Very, very important. What is the use of laminations? Yes, very good answer. To reduce the eddy current losses. What are the use? To reduce the eddy current losses, we are going to laminate the core. Sir, how eddy current losses reduces due to laminations? Actually, due to laminations, the volume of the core reduces. Which reduces? The volume of the core reduces. Volume of the core reduces. If volume reduces, what happened? We know that the resistance R is equals to rho L by A. If multiplied and divided with L, area into length nothing but the volume. Yes or no? Area into length nothing but the volume. If volume reduces, resistance increases. If volume reduces, resistance increases. If resistance increases, we know that if resistance increases, the current reduces. What is that? The current reduces, which is called as eddy currents. The currents reduces. If currents reduces, we know that eddy current losses is equals to IE square R. Eddy current square into R. If current reduces, eddy current losses also reduces. So, what is the use of laminations? Due to laminations, the volume of the core reduces. Okay? If volume reduces, what happened? If volume reduces, resistance increases. Okay? If resistance increases, what happened? Eddy currents reduces. If eddy currents reduces, eddy current losses reduces. That's why we are going to make a laminations. That's why the core is laminated. And next one, silicon steel. Why we are preferring silicon steel here? Tell me, why we are preferring silicon steel? What is the advantage due to silicon steel? Yes, very good. Due to silicon steel, the hysteresis losses reduces. What happens, sir? Hysteresis losses reduces. How it will reduces? Generally, we have a formula. Hysteresis losses is equals to neta into B max whole power x into F into V. V is the volume, F is the frequency. Here, X is the hysteresis coefficient. What is that? X is the hysteresis coefficient. Hysteresis coefficient. If X value reduces, automatically hysteresis losses reduces. If X value reduces, automatically hysteresis losses reduces. How X value reduces? For silicon steel, X value is very, very less. Sir, what is the actual range of X value? What is the actual value of X value? Generally, this X value 1.5 to 2.5. The hysteresis coefficient value 1.5 to 2.5. When we are using silicon steel, this X value just 1.6. When we are using silicon steel, this X value just 1.6. The minimum, actually, the minimum value. If X value reduces, automatically hysteresis loss also reduces. If X value reduces, hysteresis loss also reduces. So, by using silicon steel, we can reduce hysteresis losses. By using laminations, we can reduce eddy current losses. Right, sir. Now the question. Here, silicon added to the steel. How much percent of silicon added to the steel? Generally, 3 to 5% of silicon added to the steel. How much percentage? 3 to 5% of silicon added to the steel. Sir, if more silicon added to the steel, what happens? If more silicon added to the steel, the brittleness of the core increases. If more silicon added to the steel, the brittleness of the core increases. If brittleness of the core increases, what happens? At higher voltages, the core gets break down. At higher voltages, the core gets breakdown. That's why don't add more silicon. The silicon required here is just 3 to 5% of actual value. Nothing but 3 to 5% of silicon, around 95% of steel. 95% of steel. That is enough. And here we have another advantage. Here we have another advantage due to this silicon. What is the advantage? Actually, this steel is a pure conductor. This silicon is the semiconductor. When silicon added to the steel, the conductivity reduces. Conductivity reduces nothing but eddy currents reduces. If eddy currents reduces, eddy current losses also reduces again. This is the additional advantage. Right? But don't exceed 4 to 5%. If you exceeded that 5%, it leads to more brittleness. It leads to breakdown of the core at higher voltages. Right, sir? Okay, what is final conclusion? Generally, laminations are used to reduce the eddy current losses. Silicon steel used to reduce the hysteresis losses. If they are asking especially if silicon added to the steel, we can reduce eddy current losses also. If silicon added to the steel, we can reduce eddy current loss also. If they are asking like a question, silicon steel used to reduce hysteresis losses only. Hysteresis losses only. Laminations are used to reduce eddy current losses. So whatever, finally, this is about the stator core. Stator core made up of CrNGO silicon steel laminations. The silicon steel laminations used to reduce hysteresis loss and eddy current losses. How much silicon added? 3 to 5%. If more silicon added, brittleness increases. Yes or no? What is thickness of plates? 0.35 mm or 0.5 mm. This is simply what is our stator core. Now, another small topic. Generally, see here, in stator core, we have a different slots. We have a slots in which the winding is placed. We have a different types of slots. Now tell me, how many types of slots are there? Tell me, how many types of slots are there? There are 3 types of slots. What are those? Open type of slots, semi-open type of slots, and closed type of slots. Let's see about those. Open type, semi-open type, and closed type of slots. Let's see what are the different types of slots here we have. Okay, so we have 3 types of slots. Open type, semi-open type, and closed type. Right. Open type, nothing but how they are looking like this. These are called as open type of slots. And semi-open type of slots. Semi-open type of slots. These are semi-open type of slots. It is also called as semi-closed or semi-open. And last one, closed type of slots. Closed type of slots. These are called as closed type of slots, in which we are going to place a winding. Okay, open type, semi-open type, closed type. Now tell me first one, which is very easy to place the winding and remove the winding. Which is very easy? Yes, very good. This is easy to winding procedure. Easy winding procedure. What about here? Difficult winding procedure. Difficult winding procedure. What about here? Very difficult winding procedure. Very difficult winding procedure. Very difficult winding procedure. Right. Okay, next one. In which of the following case air gap length is more? In which of the following case air gap length is more? Here air gap length is more. Here air gap length is medium. And here air gap length is less. Air gap length is more, medium, less. If air gap length is more, reluctance also more. What is the formula? Reluctance S is equals to L by mu A. Yes or no? If reluctance S is equal to L by mu A, if air gap length is more, the reluctance also more. If the air gap length is medium, the reluctance also medium. If air gap length is less, reluctance also less. Reluctance also less. And here, generally here, if reluctance is more, the leakage flux is less. Here, leakage flux is medium. Here, leakage flux is more. Leakage flux is more. And also, last one, very important one. In open type of slots, power factor is less. In semi-open type of slots, power factor medium. In closed type of slots, power factor is more. The power factor is less in open type of slots. The power factor is more in closed type of slots, medium in semi-open type of slots. And also, here air gap length is more. That's why here harmonics also more. Harmonic components also more here. Here harmonic components are medium. Here harmonic components are less. Here harmonics are less and power factor is more. Here harmonics are more and power factor is less. Here both are medium. Okay? What is first one? Easy winding procedure. And next one, the air gap length is more. If air gap length is more, reluctance is more, then leakage flux is less. Here power factor is less. Power factor is less, and also here harmonics are more. Okay, now see here the very important points are easy winding procedure one and low power factor one and high harmonics one. And here very difficult, of course, but power factor is maximum. Of course, harmonics also less. Now tell me, for our induction machine, which is preferable? Tell me, for our induction machine, now which is preferable? Sir, for induction machine, power factor is very important factor. We should select the slots with a high power factor. That's why closed type is much important, sir. That's why we prefer mostly closed type. Of course, in closed type, power factor is better. That's why this is preferable. Of course, but what about here? The winding procedure is very difficult, which is costly and complex. Now tell me, if it is used here, this is costly and complex method. But if it is used here, the power factor is less. Now tell me, which of the following is preferable in our induction machine? Right, very good. For our induction machine, semi-open type of slots are preferable. For our induction machine, semi-open type of slots are preferable because normal difficulty. It is not much complexity and not high cost. Just medium complexity, medium cost, as well as medium power factor, as well as medium harmonics. That's why generally in our induction machine, we are using semi-open type of slots only. We are using semi-open type of slots only. Okay, in induction machine, we are using semi-open type of slots. Right? But they are asking question. I am using my induction machine in laboratory applications. I want accuracy, more accuracy. Even though difficulty, even though complexity is there, no problem. I want more power factor, which is used in laboratory. Now tell me, which of the following slot is preferable? Tell me, sir. In laboratory application, which are using induction machines, in those applications, we are using closed type of slots. These are used in small induction machines, which are used in small induction machines, which are used in laboratory applications. Small induction machines, which are used in laboratory applications. Which are used in laboratory applications, we are using closed type of slots. But in generally in induction machine, we are using semi-open type of slots. Can you tell me what about DC machine and synchronous machine? Can you tell me? What about DC machine and synchronous machine? In DC and in synchronous machine, we are using open type of slots. You can study it DC and synchronous machine, why we are using open type of slots. But in induction machine, for medium difficulty, medium complexity, and for medium power factor and medium harmonics, that's why in induction machine, the semi-open type of slots are preferable. But in small induction machine, which are used in laboratory applications, we are using closed type of slots. We are using closed type of slots. This is about generally the different types of slots. Okay, whatever. In stator, we have a slots which are semi-open type of slots, In rotor, we have a slots which are semi-open type of slots. Both the slots are semi-open type of slots only. Okay, both are semi-open type of slots only. Okay, sir. Next one. These slots are inner periphery slotted or outer periphery slotted? In stator, which side is slotted? Inner periphery or outer periphery? In stator, inner periphery is slotted for winding. But in rotor, outer periphery is slotted for winding. In stator, inner periphery is slotted for winding, and in rotor, outer periphery is slotted for winding. Okay, sir. In induction machine stator, which type of winding we are using? In induction machine stator, which is stator winding. The stator winding is a short pitch concentrated, short pitch distributed winding. In induction machine stator, we are using a short pitch distributed winding. We are using. In induction machine stator, we are using short pitch distributed winding. Very important. Very, very important. Right, sir. Next, this is simply about the stator core. Stator core made up of CR silicon steel laminations. Inner periphery is slotted for winding. In those slots, we are placing a short pitch distributed winding. And different type of slots, we know that. And we are going to laminate the core? You know that, to reduce the eddy current losses. Why we are going to use silicon steel only? To reduce the hysteresis losses. How much percent of silicon added? 3 to 5%. If more percent of silicon added, what happened? Brittleness increases. It may lead to breakdown of the core. Right? What are the thickness of laminations? 0.35 to 0.5 mm. Due to laminations, volume of the core reduces, then eddy current losses reduces. This is finally about the stator core. Completed. Okay, next one. Third one. What is this? Air gap. I already given you. Third one. Air gap. Tell me, in any electrical machine, if air gap length increases, what happens, sir? I mu, magnetizing current increases, and I naught, no load current increases. Magnetizing current increases, no load current increases, and power factor reduces. In any electrical machine, if air gap length increases, I mu increases, I naught increases, power factor reduces. We already discussed differences between transformer and induction machine. Yes or no? Yes, we already discussed. Generally, in induction machine, air gap length is greater than the transformer air gap length. In induction machine, air gap length is greater than the transformer air gap length. In induction machine, air gap length is less than air gap length of synchronous machine. The air gap length, the order of air gap length. In transformer, air gap length is less. In induction machine, air gap length is greater than transformer. In synchronous machine, air gap length greater than induction machine. Nothing but the no load power factor of induction machine. The no load power factor of induction machine less than transformer but greater than synchronous machine. Less than transformer but greater than synchronous machine, because if air gap length increases, power factor reduces. The transformer having the least air gap, nothing but high power factor. This is very important in any electrical machine. If air gap length increases, power factor reduces. In our induction machine, air gap length less than synchronous machine and greater than the transformer. This is about air gap, very easy, right? Air gap. And next, fourth one, rotor core. Rotor core. Let's discuss later. And fifth one, tell me fifth one. What is fifth one? Fifth one is the shaft. What is a shaft? Let's see here. Shaft. Next one. Shaft. Tell me, sir, shaft made up of. The very important. This is only the question they are asking. Shaft made up of mild steel. Generally, we are using mild steel, or it is also we are using nickel alloy. Mild steel or nickel alloy, but in generally we are using mild steel to make the shaft. Okay, shaft made up of mild steel. And next one is there slip rings. Tell me, slip rings made up of. The slip rings made up of hard drawn copper. Slip rings made up of hard drawn copper or phosphorus branch. Slip rings made up of hard drawn copper or phosphorus branch. Shaft made up of mild steel and slip rings made up of hard drawn copper or phosphorus branch. Right, okay. Next one. Generally they are asking question. In three-phase synchronous machine, how many slip rings we are using? In three-phase slip ring induction machine, how many slip rings we are using? In three-phase squirrel cage induction machine, how many slip rings we are using? They are asking question like that in competitive exams. Tell me, in three-phase slip ring induction machine, how many slip rings we are using? 3 slip rings. In three-phase squirrel cage induction machine, no need of slip rings. In three-phase squirrel cage induction machine, 0 slip rings we are using. What about synchronous machine? In three-phase synchronous machine, we are using just 2 slip rings. Sir, how, sir? Actually, this is a three-phase synchronous machine, but you are telling that only 2 slip rings. How it is possible? Generally, in synchronous machine, the stator given by three-phase AC supply. In synchronous machine, stator given by three-phase AC supply, but rotor given by just DC supply. In synchronous machine, stator given by three-phase AC supply, but rotor given by DC supply. DC nothing but one is positive, one is negative. One slip ring and another slip ring. Just we have 2 slip rings. Yes or no? Just we have 2 slip rings. So for three-phase synchronous machine, we have 2 slip rings. For three-phase slip ring induction machine, we have a 3 slip rings. And for three-phase squirrel cage induction machine, we have a no slip rings or 0 slip rings. 0 slip rings. This is simply about slip rings. They are asking question, right? So slip rings made up of hard drawn copper or phosphorus branch. The shaft made up of mild steel. For example, they are asking question, the brushes made up of, can you tell me what is answer? Brushes made up of carbon, graphite or copper. Carbon, graphite or copper. Brushes made up of. In generally, we are using carbon or graphite. For high rating applications, we are using electrographites. So now they are asking question, why we are only preferring carbon or graphite? Why we are only preferring these two? Because of self-lubricants property. Because of self-lubricants property, generally we are using carbon or graphite brushes. Generally, this is more used in DC machine. We can study more detail in DC machine. Why we are using carbon or graphite brushes only? What is the use of these two brushes rather than copper? We can explain there. Right? So whatever, generally brushes made up of carbon, graphite or copper. Generally for high rating applications, we are using electrographite. Because of self-lubricants property, carbon and graphites are more preferable than copper. Copper used for low rating machine. Size, the brushes. This is generally about brushes. Okay, so I tell you that brushes, slip rings and shaft. Brushes made up of carbon, graphite, copper. Slip rings made up of hard drawn copper or phosphorus branch. Shaft made up of mild steel. Right, these two. Then after, first one stator frame completed. Second one stator core completed. And third one air gap completed, and fifth one shaft completed, and next one slip rings completed, and brushes completed, and next and last one rotor core. That is fourth one, rotor core. Now rotor core. Rotor core made up of CRNGO, silicon steel laminations. The same. In rotor core, we have a slots which are open. Which type of open? Semi-open type of slots. We are using. Rotor core made up of CRNGO silicon steel laminations. Okay. Next one. These are also semi-open type of slots we are using. Okay. And next one. Generally, the rotor inner periphery slotted or outer periphery slotted. The rotor outer periphery slotted for winding. Outer periphery. Stator inner periphery slotted for winding, but rotor outer periphery slotted for winding. Yes. Next one. In induction machine, we have two types of rotors. In induction machine, we have two types of rotors. What are those two types of rotors? Slip ring induction rotor. And next one, squirrel gauge. squirrel cage induction rotor. Slip ring induction rotor, and next one squirrel cage induction rotor. These are very important. Slip ring induction rotor, and next one squirrel cage induction rotor. Slip ring induction rotor and squirrel cage induction rotor. Now we have to discuss these two rotors, very important. Okay, so up to here just rotor core made up of CR silicon steel laminations. In rotor also we are using semi-open type of slots. Generally in rotor outer periphery is slotted for winding, right? And next one, here in rotor we have two types of rotors in induction machine. Those are slip ring induction rotor. Slip ring induction rotor is also called as wound rotor. It is also called as wound rotor. And another one squirrel cage induction rotor.